Right, welcome back. So we're on our way to building a quantum conformal field theory, and we've so far been looking at the consequences of conformal symmetry on the observables of a quantum field theory. So the observables of a quantum field theory are the correlation or Green's functions. So these are things that look like this. And these are not directly observables in the sense of observables in quantum mechanics. They're not Hermitian operators, because if you take the dagger, then you can not always is this operator here Hermitian. But they're directly related to things that you can observe in experiments, namely scattering amplitudes. You have m particles in and n particles out, for example. And these kind of scattering experiments, these are operationally well-defined things. Take some particles, collide them, look at what comes out. And from that you can infer these correlation functions. So, well, not directly observable, they are at least indirectly observable. Now we've noted so far that if you have a quantum field theory, let's suppose by magic we are handed a quantum conformal field theory, someone claims it's conformal. We've noted that for conformal field theories, these 2 and 3 point correlation functions have a very particular behavior. This is alpha and beta. So for these things called primary fields, these correlation functions have this very characteristic polynomial decay type behavior here. And alpha has to equal beta. And similarly, we've derived something for the 3 point functions. Now that's all fine and good, but we don't actually have yet a quantum conformal field theory. We have the promise that if we had such a quantum conformal field theory, then the correlation functions must look like something like this. But that doesn't actually give us a quantum conformal field theory. And so our next job is to construct a conformal field theory. We've seen, more or less we know what to do classically to build a conformal field theory. You can write down actions which are invariant under dilations, and that should do the job. Quantumly, it's not so clear. Right? So we have this box. There's a very useful box in field theory called the path integral. And this box, you hand it some classical data, and it will return you some quantum data. Well, some potentially quantum data. So what you get from the path integral prescription here is a formula for something that's very much related to one of these endpoint functions here, namely the time-ordered version of one of these endpoint functions. So one way to go about constructing a quantum conformal field theory, at least at the sort of physicist level, is to start with the classical conformal field theory, put it into the path integral, and hope sufficiently hard that nothing gets broken on the way. Now, path integrals can be treacherous. Symmetries that are true for a path integral might not be true for the corresponding quantum theory. It might be that what comes out here is not even observables for a quantum theory. There are various ways in which the path integral prescription can go wrong. And so it's more of a discovery tool. You can use it to very efficiently find formulae for putative quantum theories, and then you can systematically verify various properties of these observables. And then once you know enough about the resulting quantum theory, you can try and construct it in a different way if you don't trust the path integral. So, but it is a very efficient tool, even though it may not be rigorous, and that's why we're going to use it, exploit it to understand how to build quantum conformal field theory. So we're not going to quite build a quantum conformal field theory in this, or probably even the next lecture, but we're going to see how to take a classical action with conformal symmetry and see what the operators are that do the conformal transformations. So the goal, which we started in the previous lecture, so we take as input a classical conformal field theory, which are relatively easy to build, relatively. And then we're going to use the path integral to output the quantum generators we can use the path integral to output the quantum generators for the conformal symmetries for some hopefully quantum field theory. And at that point, you're more or less done. When you can do that, you have all the generators that can do all the symmetries, and one symmetry of all quantum systems is time translation. So that's the Hamiltonian. So as a consequence, you'll get out a Hamiltonian from this prescription. You'll also get out the generator of spatial translation, the generator of dilations, and so on. And from that, you can answer a great many questions about the theory. That still won't yet quite present an example of a conformal field theory. Our last step in constructing a quantum conformal field theory will be to collect some actions for classical conformal field theories and then just deploy this procedure. We're not going to do that today. Our first example, probably the construction of this example will probably occupy us for the rest of this course, and it'll be the simplest possible example you can imagine, namely the free boson. But it turns out to be a lot of intricacies in applying this prescription. But the benefits are quite considerable. Understanding the free boson example, which we'll study, will lead you to understand quite an array of examples of quantum conformal fields. So you don't really lose tremendously much. Good. So let's now get to how do we find the quantum generators of a conformal symmetry. So I briefly sketched that at the end of the previous lecture. If you have some classical action with a classical symmetry, then there exists a prescription to find the quantum implementation of that symmetry, and we exploit the path integral. So just a note on how we're going to do our calculations. We're going to work with a so-called imaginary time. I've touched on this in previous lectures. That's for two reasons, really, in this course. I think the first is just it's convenient. It's convenient for a number of reasons, one of which is things converge better. And there's sort of other reasons to think that it's a convenient thing to do to work with imaginary time. A second reason, and this is not to be underestimated, is that we can make direct contact with statistical physics. So rotating time to minus I beta t is a very useful thing to do because it turns all the formulae that would normally be valid for a quantum system and unitary time evolution into statements about partition functions and systems at some temperature beta. And it'll turn out that the biggest source of examples of conformal field theories will come actually not from unitary representations of the conformal group, but from statistical physics theories close to a phase transition where the symmetries are represented by, non-unitarily represented by replacing t is minus I beta. I'll just show you how that, just remind you of how that works, right? So suppose you have the generator of time translations, that's the propagator. The propagator is e to the minus I t h. And if you analytically continue time to imaginary time and set t equals minus I beta, then the generator of time translations becomes non-unitary. So this is something you have to be. I guess we'll call it S of t. So t equals minus I beta replaces the unitary generator of time translations with this non-unitary semigroup e to the minus beta h, with the fixed point being the ground state. So this thing here gives you information about the thermodynamical quantities of this system. So if we put this system in contact with the thermal reservoir at inverse temperature beta, then this object here tells us all the thermodynamics of such a system. You can just take the trace if you want of this object and you get the partition function, and from there you learn all kinds of things. And one thing I'll touch upon possibly towards the end is that for systems, this gives us a good guide where to look for conformal field theories. Systems that come close to a critical point, systems that reach a phase transition, will enjoy a larger symmetry at the phase transition point. This is not something I can prove to you, but it's an observed fact. And that enlarged symmetry will include dilation in scale invariance. And so it's sort of a good conjecture to think that phase transitions are in fact examples of conformal field theories, but not unitary representations of the conformal group, because this translation generator is no longer unitary. But if you're willing to just accept that, then this is an interesting place to look for conformally invariant systems at a phase transition. I guess that's really a topic on its own. I'll just give you a reference. There's a book by Cardi on scaling phase transitions. Where these ideas are explored in their fullest. Our goal in this course is more to construct unitary representations of the usual conformal group of Minkowski space. We'll do that via this expedient of going to imaginary time and then at the end going back to real time. So it's called Wick rotation. So when you do Wick rotation, all your path integral formulae change slightly. If t goes to minus I beta, then this path integral up there, we lose the I and we get a minus sign. There's a third reason, and that is, which is sort of about convenience. It's easy to actually numerically evaluate such path integrals. When you've got a minus sign here, you typically don't have a sign problem. You can sample them, and you can numerically evaluate correlation functions and see if they have the required scaling behavior of a conformal field theory. And from that, you can read out conformal data like the dimensions of these primary fields and other things. So these are very good reasons to want to work with the Wick rotated version Just think of it for this part of this course as a convenient substitution. We'll work with t as I beta until the last minute when we'll say beta is it. And all our formulas should be holomorphic enough to let us do that without encountering any obstructions. So let's go back to the job of constructing the quantum generators of conformal symmetries. So we're going to suppose So we're going to start with some classical fields, and we're going to assume we have like a vector of them or a tuple of them. Maybe they're spinors or maybe they're tensors. I don't know. You just have a list of fields, and this phi of x is meant to be that list of the fields. And this is all classical so far. Then the path integral prescription says if you have an action for these fields, so that's the action for these fields, the path integral prescription gives us a way to invent correlation functions for quantum versions of these fields. Now, we're not going to just take any old action. We're going to take actions that are sufficiently symmetric, ones that are invariant under lots of symmetry transformations. Because if we can't even have a classical theory that's invariant under conformal symmetry, then it's not really a good place to look, is it? We should start with something that we think is conformally invariant. So we're going to suppose that our action is invariant under some infinitesimal symmetries. Be invariant. So our action is going to be invariant under a bunch of symmetries like this. Now, we've covered the infinitesimal versions of conformal symmetries in classical field theory in a previous lecture. So we worked out what these G's look like. This G looks like there's a delta A, right, coming from the dimension of the field, and then there's a temporary block minus I x mu. Minus I. So we've seen the generators for all the conformal symmetries, and there's formulae for all the others. I mean, translations, this is just minus I x minus I delta nu for translations, and similarly for all the rest, right? So we have a theory. We know what symmetries we want it to be invariant under. We want it to be invariant under the whole host of conformal symmetries. So we have an action, it's invariant under this, but it's all classical. So let's just do the simplest thing and just hope that it works, and then see what are the consequences of this action. So the simplest thing we could do is to just stick that action into the path integral and see, well, what is the consequence of these symmetries? Do we get a quantum theory? Do we get a quantum theory invariant under conformal symmetries? And under a fairly straightforward set of criteria, we will be able to say we should get a quantum theory with conformal symmetries. I didn't say it, but this omega is infinitesimal. Let's go. Let's see what's going to happen. We already sketched it out in the previous lecture. You write out the path integral. You make an infinitesimal symmetry transformation, see what happens. So we're going to look at endpoint correlation functions of a putative quantum theory. So we're going to build this thing here. X hat just stands for a product of the quantum field operators at endpoints. I don't know if these quantum fields exist, but the path integral prescription says that here's a formula for them. Now we're going to be have to be a little bit more careful, right? The path integral prescription doesn't give you just the product of a correlation function of the product of the fields. It gives you the time-ordered product. So we'll let X have the time ordering there. I'll probably forget the time ordering from now on. So I'll just make a note here. Okay, so whenever I write down something with the left-hand side and the right-hand side, and the right-hand side is a path integral and the left-hand side is a correlator, you know that it's time-ordered, not just any old correlation function. So we have this formula here. The correlation function, if we believe the path integral prescription, then that time-ordered correlation function ought to equal that path integral there. So when you do I should comment on this. When you do Wick rotation, the bottom path integral here turns out to be equal to trace of e to the minus beta h, which is the partition function. So this path integral prescription here, when we have t is I minus I beta, is something over the partition function. And to make our life easier, we just write that as x. So that's why I was commenting about this time ordering. The x without the hat is just the product of the fields at endpoints. The x with the hat is the time-ordered product of these fields with the hats. So now we're going to say, let's do one of these infinitesimal symmetries that we assume our action has. And in order for this to have any hope of working, we need that this path integral measure is invariant under the symmetry. So suppose, and it's a big suppose, that d phi prime equals d phi. So phi prime is defined by this equation here. Call it star. So there's no reason this could be true, should be true. In fact, when symmetries become anomalous in quantum theories, it's exactly that fails. One has to always be a little bit careful, but let's just assume that everything's going to be nice. You know, you have two ways of treating Mother Nature. One is as an adversary and one is as your friend. Here we're going to assume nature is going to be friendly to us today. and that the physical theories will have that nice property. And then let's just do this symmetry transformation star on this path integral here. Well, the bottom, nothing happens to the bottom, right? Because the action's invariant up to a total derivative, which then goes away. But the top's slightly more subtle. So each of these fields under this transformation here, phi prime is equal to phi minus blah, 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 each of these fields gets changed a bit. So we'll write that change to first order as dx. And also the action is also allowed to change, right? A classical symmetry doesn't leave the action completely invariant. A classical symmetry leaves the action invariant up to a total derivative. We'll use the Lagrangian invariant up to a total derivative, sorry. There we go. So that's the result of doing an infinitesimal symmetry transformation. So it's sort of hard to overemphasize how useful the path integral prescription is for doing symmetry transformations in quantum theories. Because you have a classical theory on one hand with its classical symmetries, and then you try, quantization is this act of guessing a quantum theory that corresponds in some moral way with the classical theory. And that the classical theory has some symmetries doesn't lead you anywhere towards guessing a quantum theory that has a bunch of symmetries. So the path integral is really a lovely way of guessing, actually guessing quantum theories with a bunch of symmetries that match or are analogous to their classical counterparts. And I don't really know as nice a way to do this in any other way of guessing quantum theories. So this we've seen already in the previous lecture, just doing it a bit slower and in this Wick rotated context. So this total derivative here that we have, we've seen this also before. This is the conserved current, right? Associated with a symmetry. And that's what features in the proof of Noether's theorem, right? So this is exactly one and the same thing. So we'll take a look at this expression here. So we've got on the left-hand side, we've got some time-ordered correlation function. On the right-hand side, it's completely symmetric. We have another formula for the time-ordered correlation function. And now we look at cancelling the order 1 term. So we've got an order 1, an order delta term, an order delta squared term, and so on. Let's just cancel off the order 1 term. So let's look at the things that are infinitesimal here. So this is infinitesimal right there, the omega A. This delta x comes from the symmetry transformation on the field. So x equals the product of the fields. X plus delta x is the same thing, but now in terms of the transformed fields. So this is, well, let's just write as x prime first. This is the field at the first location, field at the second location, so that's the transformed version of x. And then we can write out x prime to first order in these infinitesimal generators, omega. Oh, sorry, I'm doing the transformation passively. So this is a minus. So I don't want to use prime for transformed. Twiddle. X twiddle is what happens when we replace phi with the infinitesimally transformed phi. And then let's just collect x twiddle to order epsilon, order omega. Omega is the small thing here. Well, it's going to be x, right? If you drop all the infinitesimals, you get just the original thing again, plus delta x. That's the first order contribution. And the first order contribution is the following. So delta x then equals minus I, the sum of j over all the locations times omega. So this is just the first order. If you expand that out to first order, that's the term you collect. And then we can also use this observation here to write the right-hand side to order omega. So let's just expand out this expression now to order omega and see what we get. So the right-hand side equals 1 on z d phi x e to the minus I s of phi. That's the order 1 term. So that's our original correlation function. Plus, now let's do this order epsilon contribution here, or order omega contribution here. Okay. But there is another contribution to order omega that we have to take account of. A minus sign error there. And that is, this term in the exponent is also order omega. So we should expand to that term as well and add it in to the expansion. So that gives this term, but with this expanded to first order. And that all equals x hat. Right, that's just an expansion. But now we can look at the three terms that we have here on the left, the right-hand side and the left-hand side, and we can compare them, right? So this term here, that's what we had originally, so that really is just x hat. So the order 1 terms cancel, as they better do. This next term here is the path integral quantization of this, of something called d hat x. And the last thing here is the path integral quantization of something that we would call d mu j hat mu times x. So j depends on the fields, right? The current depends on the fields. So when you put it inside a path integral, you're finding the quantum version of it. So it's j hat mu a. And then these other operators didn't go away, they're still there. And so if you evaluate all this to order omega, you get a very compact expression. Now I've let omega depend on x. So when you prove Noether's theorem, the action's only invariant under symmetries generated by a constant omega a. But if you allow omega to depend on x, this formula is still correct to first order in omega. So that's just something to bear in mind, that omega need not be constant for this formula to still be correct. This is a very useful observation. Because this is just Taylor series here. Taylor series of the action under the symmetry. And the fact that we don't need omega to be constant for that formula to be correct is actually a very important fact that allows us to pull out a definition of the local generator of these symmetries. So let's just take these left-hand side and right-hand side and see what it tells us to order omega. And it tells us something non-trivial. It has some bite to it, this expression, because it tells us that two things must be the same. It tells us that the quantization of delta x had better be the same as the integral of the divergence of the quantization of j hat x hat. That's the consequence of all that stuff. That's what we've learned. This is tremendously useful because this is a local quantity that only depends on space-time location x. And this is the variation in the fields. And we know that these currents, this is a conserved current here, this J A mu, if you integrate them over time, then you get the charge, the conserved charge, which generates the symmetries. This is very useful fact. But also it's local. This thing here is local, and we want to find local generators for our symmetries. Now if you take a look at this delta x, I wrote a formula down for it up there. There it is there. Delta x equals minus I, the sum of all those things, omega a xj. But we can write that in another way, which is rather convenient, by introducing delta functions. And that'll help us pull out this local aspect of this thing here. I mean, it's just the same thing, right? If you look at delta x up there, it's just the sum of the fields, except at the jth place where you put in the generator of the symmetry. And this is exactly the same. All I've done is put an integral over the x, and then, in order to make sure that that this omega here is evaluated at the right place, I put in a delta function. So it's just doing nothing. But this is very convenient because on the right-hand side of this expression here we have an integral over x, and now on the left-hand side we've got an integral over x. And that is what allows us to write down the following local relation between how the fields transform locally and the current that generates that transformation. So this is how the fields, these are how the quantum fields transform under the symmetry, supposing this prescription works out. And that G is the generator of that infinitesimal transformation that we know, right? We put that in. And on the left-hand side, we got the current here. So this formula here this goes under the name of the Ward identity. It's our principal tool for quantizing symmetries and showing us how. So I should not have actually put a hat there. So this is our principal tool for showing how symmetries are implemented on quantum correlation functions. So this is true. If you look at the expression before it, we had this integral over x, and all we did is took away the integral sign. We said it had to be true for all omega a x. So that's the same as demanding that this is just true locally and pulling off the integral. So let's just take a look at some simple consequences of this. Suppose you integrate the left-hand side over everything. Well, supposing that everything sort of decays quickly enough here, then when you integrate the left-hand side over everything, you get 0, right? Because you've got the integral of a divergence of something, use Gauss's law. And then you realize this integral is a surface integral at infinity, but everything has decayed away, so that should be 0 if you integrate over everything. But so if you integrate over all space-time, and if you assume good decay properties of the left-hand side is definitely 0. But the right-hand side is not definitely 0. And so we get that the variation of these correlation functions so the right-hand side is very definitely 0, right, as well, right? You can't have 0 not equal to 0. So So this just tells you what we already know. Integrating over all of space-time tells you that the correlation function is invariant under the symmetry, infinitesimally. Good, right? So we haven't lost anything in this formulation, and we've gained something in that this is true locally, not just after integrating over all of space-time. And now what this does is it carries so much more information. It allows us to interpret certain things here as generators of the symmetry, as the quantum generator, as an operator which carries out or induces the symmetry. So you take the 0th component of the conserved current and integrate it over a space-time slice. You should remember that's the generator, that's the conserved charge, right? That obeys, just from the conservation law, this obeys the conservation, it's time invariant, right? We can interpret this operator here as the conserved charge corresponding to the symmetry, or the generator. And that's the other interpretation that I like, that is much more important for this discussion. Because J mu A is something you just get from looking at the action. J mu hat of A is the result of the path integral prescription. And J naught hat is therefore a formula for the generator of a conformal symmetry in terms of the fields. So remember J, the conserved current has an expression in terms of the fields. in Noether's theorem if you take a look. So we found how to write the generator of a symmetry in terms of quantum fields. We now know the quantum expression for the generator. So there's J here. If you remember the expression for that in terms of the Lagrange density, it's dl d omega dl d phi dot times omega, if you remember, plus a total derivative. So soon enough we'll do an example when we get to the free boson. Now, there's one other observation that enhances this interpretation here. And that is, if we take the water identity that we've got written out here, and we integrate it not over all space-time, but over a little thin box. So we'll call this star star. So we're going to integrate over a thin box bounded by t minus and t plus, which are infinitesimally close to each other. So on a space-time type diagram, so here's x, here's y, and here's t. Then at some given t, we're integrating over a box of width t plus minus t minus. The left-hand and right-hand side of the water identity. So this is t minus, this is a t plus. And if we do that, then we see that the left-hand side has a much more suggestive form. Ah, yeah, sorry, I didn't say things about the times. Okay, so that's the locations of all the fields in these correlation functions, x1 through to xn. Let's now suppose that x1 has time component t. I could say t1, but I'll just choose t. T equals x1 naught, it's the time component. And all the others are far away. So you imagine in this space-time diagram, there's a field living right there at time t, but there's fields here, there, and everywhere else. And we're going to call this stuff here y, the fields that aren't near the time t. And then if you integrate the left-hand side up there, sorry, the right-hand side, no, I mean the left-hand side. If you integrate that up there over this box, then you'll have a surface integral, and there'll be two parts to the surface integral. There'll be the surface integral due to the bottom part of the box, which will be this generator here, and there'll be the surface integral of the top part of the box, which will be that generator again, but at slightly different times. And integrating the left-hand side then shows us that this combination here, which is the left-hand side, it's all time ordered, so I'll just leave it with a Q on this side. Right, it's time ordered. We have a correlation expression and a path integral. So this has got to be equal to minus I g hat phi x1 hat y. So now we let beta go to infinity, and we'll see we end up with a rather interesting expression here. This is true for all beta, but it's also true for beta is infinity. When you let beta go to infinity, these correlation function expressions become vacuum expectation values. You can argue that to yourself later by just looking at the derivation of the path integral. And now, in order to get this time ordering to be just sufficiently nice to explain the result, let's assume that all the other times of all the other fields is bigger than this x0 one. And then, in the limit that t minus approaches t plus, we gain a very interesting expression. The left-hand side is a commutator, right? This is, I hope, fairly clear, right? Because of the time ordering. The t plus comes after the x1 minus. These guys are after, so this is after. So that comes in front, this one comes behind. So you have a commutator, there's a minus sign, so there's a commutator, and then you've got the actual, just the symmetry itself there. And here's where we've really won something interesting from this ward identity, because here this G is just this expression in terms of derivatives and internal labels of the symmetry transformation. But Q is a quantum operator when you commute it past that field operator, will do that symmetry transformation. So this is true for all y. So we learn that it's legal to take away the expectation value. And we gain this expression here. So this was the main objective. From classical information, we get handed an expression for a quantum operator, which when you commute it past the field operator does the symmetry transformation. So we'll just think through some basic examples to make this a bit more concrete. Let's think about spatial translation, for example. Just translating in space. So the right-hand side is pretty easy when you translate in space. G is just the derivative operator. Translation symmetry is a pretty simple symmetry. Phi prime of x is phi of x minus d mu, some fixed displacement vector. Okay, that's what translation symmetry looks like. And so that tells us what G is. G is I times d mu. In this case, A, this index A is just mu. And epsilon is omega. And so we learn that we have on the right-hand side, the generator of translations, how the field shifts under an infinitesimal translation. And then we learn that there exists a quantum operator expressed in terms of the fields that when you commute it past that thing does exactly this. So we know what that's called, right? That's the total momentum operator. Call it p hat mu. Now the total momentum operator for a quantum field is not a trivial object, right? We spent some time in canonical quantization building that thing and checking that it does the right thing. But here, it's like a general purpose formula for what this thing is in terms of the field. The way to work out what the total momentum operator for a quantum field is via this path integral ward identity method is you start with the classical action, do a translation, look at how the action changes, find the conserved current associated with translations, all classical so far, all standard procedural stuff. And then you put hats on everything, and then you're done. So after you integrate over time. So this doesn't hold just for the total momentum operator. This holds for any symmetry up to the conditions that I stated, right, that the measure is invariant. So let's just carry this out for conformal symmetries. Let's work out all the Qs, all the generators of conformal symmetries, and what they look like. We're in a position to do that now because we have the conserved currents for all the conformal symmetries. We worked that out previously. We know the generators of conformal symmetries. So we can work out what the quantum generators of conformal symmetries look like. So we just have to go through the catalogue of those things that we call conformal symmetries. If you remember, at order 1 there are translations. At order epsilon there are rotations and dilations. And at order epsilon squared there's the special conformal transformations. Every one of those is a symmetry of our action. Well, we hope it is, right? Because we've chosen a conformally invariant action. Every one of those will have an associated conserved current. Every one of those will have an associated conserved charge. And if you stick hats on it, found the generator. So let's work out translation invariance. Now you'll probably have to go back and revise Noether's theorem from your first quantum field theory course. Hopefully you remember that when an action is invariant under translations, the conserved current is a thing called the energy momentum tensor. We're going to see a lot more of this thing. So the energy momentum tensor energy momentum tensor plays a hugely important role in the study of symmetries of all physical systems, because you can express the conserved currents of all the symmetries usually directly in terms of the energy momentum tensor. So the energy momentum tensor, what is it? It's just the conserved current of translations. X goes to x plus epsilon nu. Remember, a conserved current has 4 components, so it's going to be a 4x4 thing. And conservation law means that d mu x mu, d mu t mu is 0. That's what it means to be a conserved current. And to make our life simpler, it's not actually a given, but they're going to assume that our energy momentum tensor is traceless and symmetric. This is not actually always true. It is in all the cases that we're interested in. You can always find an energy momentum tensor which does have these properties, but that'll take a couple of pages and we don't really need to worry about it since we're never going to encounter that situation. So for rotations, so we've already written out the Ward identity for translation invariance. There it is. And if you integrate over a constant time slice, you then get the conserved charge is the momentum, energy momentum operators. So now we can already jump ahead to rotations. So the conserved current for rotations can be written like this, sort of an exercise. It's not totally obvious that the conserved current for rotations can be written this way in terms of the energy momentum tensor, but you should be able to verify it fairly quickly. And that leaves us with the next Ward identity. This is a big X, not a little x. So we actually, up to now, we considered that our quantum fields were spinless. So this expression is much simpler in our cases. But here I've written out the result in a bit more generality. So the generator, how does a tuple of vectors transform? So if you have a vector of fields and you do a rotation, then it transforms according to a representation of the rotation group, which is this thing here. It's just the spin matrix representation of the jth field vector. For us, so far, we've just been setting that to be 1. We've assumed we've had spinless fields. And the third and final Ward identity, we're not actually going to bother with special conformal transformations, pertains to dilations. Yep.
Is x always a correlation function? Or
Yeah, x, oh yeah. So capital X hat here, is this always the correlation function? Yeah, whenever you see that in these kind of expressions, X hat is a product of local fields.
And on the other side,
It's also always, yeah. Here, that's also a capital X.
And the line
Oh, here, this is a little x. Sorry, yeah, this is yeah, I said it in words, but not clearly. So this is little x, and that just means the space-time location x. All right, and then I'll write out the last one, and then I think that's a good moment to pause. So, final Ward identity pertains to dilations. You can go ahead and check. Final exercise. What happens under dilations? Well, the generator of dilations, right, the G is that thing there. We worked that out a couple of lectures ago. And the Ward identity for dilations has this particular form here. That's, I think, where we'll stop. That's also an exercise. There's a couple of steps missing between each line here, because this isn't the ward identity, right? I mean, the ward identity has a derivative in it. And here I've written it without derivative. And the reason I've done so is if you look at the conserved current here, well, there's x, right? And when you hit that with a derivative, you get delta functions, and then eventually you end up with this expression here. So that's why I've written exercise there.
Did you say that the energy momentum tensor is traceless?
Didn't I say that the energy momentum tensor is traceless? Classically, yes. Yes, I did. But quantumly, it doesn't have to be. Quantumly, the energy momentum tensor may not be traceless. And in fact, that's where everything gets interesting in conformal field theory. Right. I think that's where we will stop. Yes, so in the next lecture what we're going to do is specialize, this is all for general dimensions, arbitrary dimensions, but in the next lecture we're going to specialize to 2 dimensions, which is where things are the most interesting for conformal field theory. We'll rewrite these ward identities in complex coordinates where they'll take on a rather dramatic and interesting looking form. And then in the lectures after that we will try and work out examples of energy momentum tensors for the free boson. And then we'll see that the energy momentum tensor, or the remaining degrees of freedom of the energy momentum tensor, form an algebra called the Virasoro algebra. So that's sort of the plan for the next couple of lectures. But for now, that's it. Thank you.